Welcome to class, everyone. So, as usual, this class will be recorded. Let me turn on the recording. It's not recording. Okay, so the recording has started. And I'm going to share my screen with you. Okay, so you should be able to see my screen now. So last time we got to this slide. Actually, before I even start on these slides, let me just mention something. One student in one of my earlier classes today was telling me to go back when I was showing a slide. So I said, go back to the previous slide. And after he said it a couple of times, I asked him why, and he said, it's to give me time to copy down what you wrote. So it turned out that that particular student was not aware that the slides are actually posted. So just in case there's anybody in this section who isn't aware that the slides are posted, let me just emphasize that they are, okay? So it's very important for everyone to know that each day's slides will be posted, usually a couple of hours, within a couple of hours of the class, but certainly by the following morning. Okay, so you have an exam coming up in a couple of weeks. So it's very important to be aware that everyone is expected to have studied all these slides. Okay, so after each class, what you should do is spend a substantial amount of time. I would say a typical amount of time to reserve for doing this would be about an hour after each class, just going over every slide that was presented and making sure that you actually understand that slide. Sometimes there might be a slide that you might not understand, so then you should think about that slide until you understand it. And if you really can't understand it, then you can ask me to explain that slide. Maybe we'll then meet during my office hours and we can talk about that slide. But it is very important to make sure you look through the slides and check that you understand what has been presented. So some students may be good at learning these things, or they may know a lot of this stuff already, so they may not have to spend a whole hour going over the slides for each lecture. So those students are fortunate, but on the other hand, there will also be students who may need to spend, on the average, more than an hour, right? So how much time you need to spend going over the slides will depend on the student. The important thing is to make sure you understand the material that's being presented. I'm sometimes asked if it's necessary to replay the recordings. As you know, all classes are recorded, and the answer is I don't think it's essential. It can't hurt. But it's really more important to get to read the slides. Okay, but what you could use the recordings for is if there's some slide that you can't understand, then you could replay that part of the recording and listen to what I had to say about the slide. Then that may help you to understand the slide. In fact, before you ask me for help with a slide, that's certainly what you should do. So if you can't understand a couple of slides, or even just one slide, just replay the recording and see what I had to say about that slide in class. It is very important to be aware that all the slides are posted, and you should be sure to look at the slides after each class. Even if you think you understood everything, you should still look over the slides. In that case, maybe it will take you less than an hour if you are convinced you understood everything. In fact, probably considerably less in that case. But the point is that there may be things that you thought you understood, but you actually didn't, right? So always read the slides after class. So, in fact, I can see that in recent weeks, the slides have always been posted before 11, though I see there were a couple of days in September when they weren't posted until later. Here's the date. September 2nd, the slides weren't posted until 1:29. But certainly they'll be posted by 9 o'clock the following morning, and usually long before then. All right, so back to what I was talking about on Monday. So this was the last slide that was shown. I was going a little quickly over the previous slides, so that maybe I should back up a bit more. Yes, this is a good place to start. So, as I said last time, on Monday, when the value of a variable or some other expression is a function with emphasis on the word value, how can we call that function? Okay, and the answer is you call the function using funcall, or you could use apply, but I haven't covered apply yet, but I will certainly be talking about apply later on today. So Turetsky gives a simple example from section 7.12. So here is a function, right? So the value of this expression here is a function that maps its argument to 10 times that argument. So this function is stored in a variable g by this set f. And now to call that function, you can enter funcall g12. So that calls this function with argument 12, so it returns 120. Now, as Turetsky points out in this sentence here, you cannot call that function by writing g12 like this, because this would call the function whose name is g, instead of the function given by g's value, right? So just because g's value is this function, you can't, that tells you absolutely nothing about the function whose name is g, if indeed there is even such a function, right? So if g wasn't the name of a function before, then after doing this, g is still not the name of a function. This line here is giving g a value, but it's not giving g a function definition. Okay, so a mistake which I've seen many times over the years is students writing a call like g12 in this situation instead of funcall g12. And I gave some examples on Monday to help you understand at that point. So let's suppose f is the name of a function that adds 10,000 to its argument, and g is the name of a function that adds 500 to its argument. And now this line stores the f function into the variable g. So now the value of g is the function named by f. So the value of g is the function that adds 10,000 to its argument. So now if you call g1, that is calling the function named by g, the function whose name is g. So that just adds 500 to its argument. So you get 501. If, on the other hand, you call a funcall g1, then you're calling the function given by the value of g. In other words, you're calling the f function, right? The value of g is the function named by f. So that's why you get 10,001. If you call funcall hashquote g1, well, the hashquote g has as its value the function named by g. In other words, this function here, the add 500 function. So that's why you get 501. Okay, so make sure you understand the example here. Now, so far, my examples have used functions of one argument, but you can use funcall to call functions that take 2 or more arguments. So if you want to call a function that takes k arguments, and the function that you want to call is the value of f, then you do it this way, right? Now remember, the function is obtained from the value of f, right? We are not calling the function whose name is f. We're calling the function given by the value of f. And so the values of e1 through ek are passed as arguments into the call. So here is an example from section 7.2 of Turetsky. And this example also serves to remind students that if the second argument of cons is not a list, then cons returns a dotted list. This is a very common way of creating a dotted list. I would say it's certainly the most common way that students end up with a dotted list. In this course, you're not supposed to create dotted lists, but many students make the mistake, make some mistake in their code, and they end up creating a dotted list. And the usual reason is that at some point they called cons, and the second argument was not a list. So here we are. So this value of this thing, the built-in cons function, so that function is stored in fn. So the value of fn is now the cons function, and now we're calling the cons function, right? The value of fn is the cons function, and we're passing 2 symbols. So since the second argument is not a list, you end up with a dotted list. Okay, so this is not something you do not call cons with a second argument that is not a list. All right, so you shouldn't be writing code like this. So just remember, whenever you call columns, the second argument should be a list in this course. So now let's consider the question of how we write functions that take functions as arguments. So when you're computing a call of a function g, every formal parameter is a variable whose value is the corresponding actual argument. And notice I'm emphasizing value. So the value of the formal parameter is the actual argument. So if the actual argument is a function, then the function is given by the value of the formal parameter. So to call the function, you're going to need funcall. All right. So once again, if a formal parameter p corresponds to an actual argument that is a function, then you must use funcall p to call that function. If you write a call like this or a call like this, that's wrong, right? Because in both cases, you would be calling the function whose name is p rather than the function given by the parameter p's value. And it's quite likely that p isn't even the name of a function, right? But it might be the name of a function, and it's entirely possible that you've already defined a function whose name is p, but then the function you're calling would have nothing to do with the actual argument. You would just be calling the function whose name is p. So let's look at a concrete example. So this is a function that takes as argument a predicate and two arguments to be passed to the predicate. And then yes or no, this function returns yes if the predicate returns true, that means anything other than nil. And the function yes or no returns no if this the predicate that's passed to yes or no returns nil, right? So if you pass the greater than predicate and the numbers 30 and 29, that's going to return yes, because 30 is indeed greater than 29. If, on the other hand, you pass the less than predicate, then yes or no returns no, because 30 is not less than 29. Okay. Now notice that you need funcall here, right? So over the years, I've seen many students write a function like this without funcall, just a pxy, and that's wrong. Part of the issue is that in Scheme, what I just said doesn't apply. Right? What I've been telling you applies to common lists. So all this stuff about funcall and all of these examples are common list examples. Okay, what I'm saying here is not true for Scheme, and the solutions to assignment 5 are presented in Scheme just to give you some experience of reading Scheme code, and to test your understanding, it would actually be a good idea for you to rewrite those definitions in Common Lisp. That would be a good exercise, right? That would remind you of the differences, or of some important differences between Scheme and Common Lisp. And one difference is that in Common Lisp, you need a funcall here. All right, but so let's write our own version of Maccar, and we will use the template that we should be very used to by now. So the recursive call is the obvious one. So we replace the L with the coulter of L, right? So that's the recursive call we're going to use. So that suggests that the base case should be L equals nil, right? Which is what this tests for, right? Because that's the case where the coulter of L is not smaller than L. Okay, so if L is nil, then this function returns nil, because the function should return the same result as the built-in Maccar function. And otherwise, the function makes this recursive call, and then it returns the value of the expression here, which we're going to write. All right, so this expression should return our Maccar FL. So how are we going to write this box expression? So now, to experience this program, I would just look at this and just write it out, because this is not a complicated function. In fact, I've experienced this programmer would probably write out the final version rather than the initial one. The final version will actually not even have the let. The let will be eliminated. So to experience this program, we'll just write out the final version. But since most of you are not experienced this programmers, I expect none of you would call yourselves experienced this programmers. So let's write this by considering an example. Right, so if you're trying to solve a problem, don't see the solution, then a good first step is to try a concrete example and see if you can solve your problem in that example, for that example. And then after you solve the problem for that example, you can think, well, how general is my solution, right? Does it work in all other cases? If the answer is yes, then you're very happy, you've solved the problem. And if the answer is no, then you ask yourself, exactly when does my solution not work? And then you find a way to solve the problem in cases where your original solution doesn't work. And then you repeat the process, ask yourself again, do the solutions I've come up with work in all cases? That is, are there any cases where neither of the solutions works? And if there are, then you repeat the process, right? To find, what are examples where the solutions I've come up with don't work, and then try and find a solution that works in those cases. But anyway, going back to this, so let's consider this example. Suppose the values of L and F are this list and the square root function. So we know what the box should return, right? It should return our mapcar FL, which that means it should return the same thing as mapcar, the square root function over this list. So it should return the list 3, 2, 1, 4, 0, because those 5 numbers are the square roots of these 5 numbers. All right, so the box expression should return 3, 2, 1, 4, 0. And what should X be? Well, X is our mapcar F Qudra of L. So therefore, X is the result of mapcaring this function over this list, 4, 1, 16, 0. So X should therefore be the list 2, 1, 4, 0. All right, and so this expression needs to compute the value 3, 2, 1, 4, 0 from 2, 1, 4, 0. So let's see that in writing. All right, this whole the red box should return this, right? Mapcar, the same result as mapcar FL, and X should return this, because that is the value of mapcar F Qudra of L. All right, so if L is this and F is this, then the value of X is, as I just said, this 2, 1, 4, 0, and the box is supposed to return 3, 2, 1, 4, 0. This. Now, the box expression has to compute this thing from that thing. So what do we need to do? We need to put this 3, which is in green here, at the beginning of this list. Now, where did the 3 come from? Well, the 3 was the square root of this 9. So what we need to get the 3 is funcall F car of L. So what we need to do to get this whole thing is the cons, the funcar of F car L to X, right? So cons, the result of funcall F car L to X, like this. So what we see from this is that this is a good box expression, at least in this example. Now, if you're an experienced list programmer, then you can quickly see that it's good not just in this example, it's actually good in any example where L is not nil. Okay. If you're not confident that that is the case, then you can try some more examples, either in your head, or if you find that challenging, then you can also try examples on paper, right? Don't be afraid to, it's certainly better to write things out on paper than to do them in your head and get the wrong answer, right? So doing things in your head is great if you get the right answer, but if you're not sure you can get the right answer, don't be afraid of writing things down. All right, but with experience, you'll find you can do more things in your head. All right, so this then is actually a good box expression in all cases where L is not nil. In the case where L is nil, is taken care of out here anyway, so we don't care about that case. All right, so we put this here, right? Now we're almost done, but not quite, because we've got this let that's not really needed, because the let computes this value and stores it in X, and then it only uses X once. So what is the point of storing this into X and then just retrieving it from X here? Why not just compute it just in time, so to speak? Why store something? I mean, it's better just to compute it when you need it. So we get rid of the let, and we replace this X by our mapcar F Qudra L. Okay, so we end up with this, right? So this box is exactly equivalent to this box here, but instead of the X, we have this, the value of X, right? And we got rid of the let. All right, so that's how we write our own version of mapcar. Now I'm going to explain how to write the sigma function that I told you about last time. But before I do that, let me take attendance, because otherwise I might forget. All right, so everyone who is present, would you please post present? else? If you're present, please post present. Okay, hopefully that's everybody. Let's copy that. Okay. So this is the 8 o'clock class on 27th. All right, so want to write the sigma function. Now let me first remind everyone what this function does, right? Hopefully most of you still remember what it does from last time, but if not, anyway, I'll remind you. So if the value of g is a numerical function of one numerical argument, and the values of j and k are integers, then sigma gjk returns the sum of g applied to the sum of the values you get by calling g with on each argument in the range j through k. So it gives this, right? Now, what happens if j is already bigger? If j is bigger than k? Well, then by convention, the range of integers from j through k is the empty list, right? The empty range, right? That's how we define the range from j through k, and so the sum should be 0, right? The sum of g over an empty range is 0 because you're summing nothing, all right? 0 is the identity for addition, so that's why when you sum nothing, you get 0. Just like when you multiply nothing, you get 1, because 1 is the identity for multiplication, right? That 0 factorial is 1, and 5 to the power 0 is 1. So why, right? Because you're multiplying together nothing, and the identity for multiplication is 1, right? But with addition, the identity is 0. So if you add together an empty list of numbers, you get 0. All right, so the next question is, if we're going to use recursion, what are we going to make smaller in the recursive call? All right, the natural answer is the range that you're summing over. So this function is summing over the range of integers from j through k. So therefore, in the recursive call, you want a smaller range. So there are two ways to get a smaller range, two easy ways. You can have the range from j plus 1 to k, right? That would be a smaller range. Or you could have a range from j to k minus 1, right? So both of those are good approaches, and we will use the first approach. So our recursive call will sum g over the range from j plus 1 to k. So our recursive call will compute this sum, all right? And then, as I hope you see, we want to add this to the result returned by the recursive call. So the alternative approach would be for the recursive call to compute this sum, and then add the value of this thing to the result. Okay, so now let's write this function. So as I say, the number of summands is what we're going to make smaller for the recursive call, right? K minus j plus 1 is obviously the number of summands. So using the template that we see many times, well, what is the base case? The base case is where the range we're summing over is empty. So that's where j, the lower bound, is bigger than the upper bound. So if j is bigger than k, we are summing over the empty range, so we return 0. So for the general case, we make this recursive call, right? Sum over the range j plus 1 to k. So we compute this thing, in other words. And now we want an expression that will give us the value of this whole thing from the value of this sum, right? So again, how do we write this, right? So again, we can, so in this case, hopefully many of you can see how to do this, but the general pattern is you should, if you can't see how to do it, try an example. So just pretend I don't see at once how to write this, then consider an example, okay? Certainly if you come and ask me for help writing a recursive function, that's what the kind of thinking I know. You say you're stumped, then I'll say, okay, so you're stumped. So what are you going to do? And what I'm waiting for you to say is, I'll try an example, right? But what I've actually found is many students don't do that. They just say they're stumped, and then they don't proceed to the logical next step, which is to try an example. But I'd say that what you should do is, if you don't see how to do this, then you try an example. So this is a good example. Suppose g is the squaring function, and the value of j is 3, and the value of k is 6. Then you ask yourself, what should the box expression be, and what should x be? All right. So the box expression, sigma gjk, would be the sum of the squares of the number through x. There should be 3 squared plus 4 squared plus 5 squared plus 6 squared. Right. Now, Hasanat is giving the answer. You see that, which is not what. Well, I think you've got a parenthesis mismatch there, but I think you intended only to have one parenthesis. But the point is, what I'm trying to get across is not how do you solve the problem if you see how to solve it. You see, you have students like Hasanat who see the answer, so of course then you can just write it down. That's great, right? Especially if your answer is correct. And I'm trying to what I'm trying to do here is to explain what to do if you don't see how to. So you get an exam question and you don't know how to write it. Now what do you do, right? So what I'm saying is, in that situation, then you write down the tried example, right? Obviously, seeing the answer is the best way to solve the problem. But in many cases, students cannot see the answer straight away, right? Because the students aren't experts at this kind of program. Okay, but if you can see the answer, like Hasanat, that's great, right? Then you quickly write it down and go on to the next question. That's excellent. Okay. So we try. So what was I saying? Oh yes. So the box expression, as I hope everybody sees. So even if you don't know how to do recursion, you should certainly see that the box expression in this case should return 3 squared plus 4 squared plus 5 squared plus 6 squared. Right. If you can't see this, then your difficulty is not with recursion. So that's how I often find out that students, they say they're stuck with this, and I say, well, in this case, what should be here? And they can't work it out. So a student like that is not having difficulty with recursion. Right. There's something more fundamental that is causing them not to be able to solve the problem, but the difficulty in that case would not be recursion. And what is x? Right? That's another question that doesn't depend on recursion at all, right? So you should be able to see if g, j, and k are like this, since x is defined to be this, assuming you know what sigma is supposed to do, then you know that x should be the sum of 4 squared, 5 squared, and 6 squared. Because you're summing from j plus 1, which is 4, to 6, and the function is a squaring function, right? So all I'm using there is the definition of sigma. Okay, so as I said then, this is what the box expression should return, right? Sigma gjk, right? This is the g, this is the j, this is the k, and as I also said, value of x should be here, right? Because it's sigma g, j plus 1k, and j plus 1 is 4. Okay. So x then, as I just said, should be this, right? And this box expression should be this. So now we are ready to write this thing. So how do we get this from this? And the answer is you want to add the 3 squared. Okay. So where did the 3 squared come from? It came from applying g, the squaring function, to j. So funcall g, j, right? It gives you the green 3 squared. So all you need to do is to add funcall g, j to x, as Hasanat said a few minutes ago. All right. And we can see, well, if you can't see, then you can try a few more examples in your head or on paper if necessary to convince yourself that this actually works in all cases, not just this one. In all cases where j is not bigger than k. So we substitute this thing for this. Now, once again, what I'm trying to show you is how to solve a general recursive problem. Right? So you try an example and you go through this thought process. And in this particular case, many of you may be able to just see this as Hasanat was able to, but if you can't, the approach is to try an example and find an expression that works in that case. All right, so and then the final step is to get rid of this let, because the x is only used once. All right. Now, over the years, I've set exam questions that ask people the sort of 2-part questions many times. I would say each semester I probably set at least one such question. sometimes on exam 1, sometimes on the final exam. Now, I teach more than one section, so that doesn't mean every section got a question like that, but there have been semesters where every section got at least one question like that. So this is certainly a fairly common kind of question where you're expected to have already written the function using let, and then you're asked to rewrite the function without using let, and it's supposed to be an extremely, extremely easy question. But what I've found over the years is that a surprising number of students do have difficulty with this. So let me just say, if you're having difficulty, it's not because it's a difficult problem. There must be something you missed. Maybe you didn't read the slides. I don't know exactly what. It's a totally straightforward thing, right? You just get rid of the let, and then you get rid of the x and substitute this thing. It's an entirely straightforward process. Okay, so you just end up with this. We're done. Right? So eliminating the let is very easy. All right. Now, map car on functions of 2 or more arguments. So earlier we used map car to map functions of just 1 argument, but in fact, map car can also map functions of arbitrarily many elements, arguments rather. And the important thing to remember is the number of lists is the number of arguments that the function you're mapping will be called with. So if you call map car with 7 lists, that means that the function you're mapping will be called with 7 arguments. So it better be a function that can take 7 arguments, right? Otherwise it won't work. So if your function requires exactly 1 argument, then you must have only 1 list, right? If it requires exactly 2 arguments, there must be exactly 2 lists, and so on. All right, so here is an example. So we see there are 4 lists. I'm sorry, I take that back, right? That's the output, right? So looking at this, so there are 2 lists, right? This list and this list, right? And so the function should have 2 arguments. So you must be able to call the function with 2 arguments. So what is the function? The function takes as arguments x and y, and it returns a list whose first element is the value of x, whose second element is the symbol gets, and whose third element is the value of y. And so what is the map car going to do? First, it will call this function with arguments Fred and job 1. Then it will call the same function with arguments Wilma and job 2. Then it will call the same function with arguments George and job 3. And finally, it will call this function with arguments Diane and job 4. And so you get, and then it will return a list of the 4 results. So here we have a list of the 4 results, right? When you called the function with arguments Fred and job 1, the result was Fred gets job 1, right? Because list x gets y, right? When the function was called with these 2 arguments, the result was Wilma gets job 2. When the function was called with these 2 arguments, the result was George gets job 3. And when the function was called with Diane and job 4 as arguments, the result was Diane gets job 4. Okay. Now, here's something to remember. So as Turetsky points out, if one list is shorter than the other, so for example, if you only had job 1, job 2, job 3 here, without the job 4, right, then one list is shorter than the other. Or if you deleted Diane from this list, then the first list would only have length 3, whereas the second one would have length 4. So if one list is shorter than the other, map car stops when it reaches the end of the shortest list. Now here it's important to remember that map car is dealing with the elements of the list in left to right order. So the function is first called on the first elements of the list. Then it is called with the second elements of the lists. Then it is called with the third elements. Map car stops when one of the lists has no more arguments. So if you don't have a job 4, then when map car sees that there's nothing after job 3, it's not going to try and call itself on Diane and the non-existent 4th element of this list. So let's look at 2 more examples. So this example is calling plus on 1 and 60, giving 61, and 2 and 70, giving 72, and 3 and 80, 83, 4 and 90, 94, and 5 and 100, 105. Okay. And now here is a second example that illustrates this, this if one list is shorter than the other property of map car. So first, plus is called with 1 and 10, giving 11. Then plus is called with 2 and 20, giving 22. Then plus is called with 3 and 30, giving 33. But now there are no more elements in one of the lists. There are no more elements in the first list, in fact. And so map car stops. So this is the result: 11, 22, 33. So the length of the result is the length of the shortest of the lists passed as argument. Right, so just to start to see this, map car plus 2, 3. All right. 10, 100.